Good morning, Redeemer. Greetings from California. My name is Greg Scott. I'm a science teacher at Archbishop Mitty High School in San Jose. When my sister Carolyn Roberts asked me to talk to you about light, I thought, well, she was my guiding light years ago when I decided to make the transition from the tech world into education. So I'm more than happy to return the favor. We're going to talk a little bit about light today, some of its properties, and we'll do a quick tour of the electromagnetic spectrum. So right now I'm looking around my dining room. I see the table and chairs. I see some plants outside the window. So my brain tells me that I'm seeing all these things, but really what's happening is my eyes are responding to light reflecting off all of these objects. In complete darkness, I wouldn't see anything at all. So what is it about light that makes it work? If we change the properties of light, how will that change what we see? So we're going to do a brief tour here. I'm going to start by sharing my screen. I do not miss remote learning at all, but it's handy for something like this. So I'm going to pull up something. This is an application called PhET, Physical Emulation Tools from University of Colorado. Really neat thing for looking at some of these. Here's a wave traveling along a string. If I get this thing moving, we can see this wave traveling along. You see how fast the wave travels. Light travels at a tremendous speed, 300 million meters per second. I'll pause this for a second. We can see this property of the wave called the wavelength. That's the distance between the peak of one wave to the next one. The frequency is how fast the wave is bobbing up and down. If you look at one of these green beads, just see them bouncing up and down, or see the little piston at the end here, how fast that's going. This one's going about 1.5 times per second. If I increase the frequency, the wavelength gets shorter. If I bring the frequency way down, the wavelength gets longer. Let's find a good one right about there. That's good. Stop here. You see with the lower frequency, then we have a longer wavelength. As we tour through the electromagnetic spectrum, we'll start with very long wavelengths down through the shortest wavelengths that we normally perceive. If instead of having a wave that just travels along endlessly, it reflects off the end, we can produce something called a standing wave. You see that here where the wave is in these parts, it's reflecting off at the end. There's a fixed end. There's two parts where the wave is bouncing up and down really strongly. In the middle, there's a spot where the wave is not moving at all. And we see things like this with lasers, where at a particular frequency, we get really strong amplification of the wave. You also see something like this in microwave ovens. That's why you have those really annoying cold spots where we have this node where there's no wave action at all occurring. All right, so let's take a look at the electromagnetic spectrum. So here is our electromagnetic wave. Electric and magnetic fields are constantly regenerating each other as the wave travels through the vacuum of space. We have a full spectrum of electromagnetic radiation. Out at the long wavelengths on the right side here, we can see radio waves. We go through microwaves, infrared. Visible light is a very tiny part of the entire spectrum. And then we go on to shorter wavelengths, higher energy, the ultraviolet, X-rays, and gamma rays. So out at the long end, we have radio waves. I used to listen to DC 101 at 101 megahertz. The wave was just about 3 meters long. So radio waves cover anything from thousands of meters long down to about 1 meter. Next, we have microwaves. Those go in a range of 1 meter down to a millimeter. Our father worked for Westinghouse Electric. He worked on radar systems, so he worked a lot with microwaves. Also, cell phones use these, and most of you have microwave ovens. As I mentioned before in that standing wave demo, those annoying cold spots come about because the microwaves are reflecting inside the oven. I have an extended version of this talk where you can see how you can measure the wavelength of microwaves, doing a little bit of quesadilla physics. Next, we have the infrared radiation. That covers anything from 1 millimeter down to 1 micron, 1,000th of a meter, about the size of a bacteria. This is radiation given off by warm objects. You see a picture of a human body. You see hot and cold spots on it taken with an infrared camera. Now, the James Webb Telescope has been using infrared radiation. We're seeing pictures in that have just been coming in the last couple of weeks. We're seeing amazing pictures from that. The long wavelength of infrared means that the light can pass through gas and dust clouds. We can see features that are not visible in visible light. Yeah, think of it this way. If you're out at Ocean City, those long waves passing by in the ocean will go right through you as though you weren't even there. On the other hand, if you're in a swimming pool, those little ripples will come along and reflect off you. So that long wavelength infrared will pass right through, and we get amazing pictures like this shot of the Carina Nebula. We can see through the gas and dust to places where stars are being formed. Now, this was all done in infrared. The wavelengths are mapped to visible colors so that we can see the pictures ourselves. Continuing on down, we get to visible light. This wavelength is in the, we call the nanometer range, 10 to the minus 9 meters, anywhere from 700 to 400 nanometers. So this is a radiation given off by very hot objects. There are also instruments like LEDs and detectors that use these transitions between electron energy levels. I'll show that in a moment. As well as being a wave, you can think of light as a particle. There are little packets of energy. When there are transitions of the electrons in an atom from one energy level to another, they can either absorb light or emit light. LEDs are an example of taking high energy electrons, having them drop to lower energies and emitting light. On the other hand, solar cells will take the high energy light coming in from the sun, the visible light, and absorb that energy, knocking electrons into higher levels where you can get the electrical energy out of them. Also, with visible light, we have photosynthesis going on. All those hardworking plants outside are using that energy from the sun to tear apart the water molecules. They use that high energy to in turn rip apart carbon dioxide and put it all back together to make sugar molecules. And in turn, it gives us the oxygen that we can breathe. Continuing on down in the spectrum, ultraviolet radiation is the next higher energy. It's shorter wavelengths, higher frequency. This is ionizing radiation. The packets of light, the ultraviolet photons, have high enough energy that they will break bonds between molecules. This is particularly important for us if we are exposed to too much ultraviolet light. It can cause sunburn and skin cancer as it tears apart the DNA in our skin. Higher energy still, we get down to X-rays. Now the wavelengths are coming down to as low as 0.01 nanometers, so the size of an atom. These are absorbed by very dense tissues such as bones, so we can use X-rays to take pictures inside the body. Many medical and scientific applications. Going down even lower, we have gamma rays, extremely high energy. These wavelengths get down to the size of the atomic nucleus. They're produced by nuclear reactions. They're extremely dangerous. They can penetrate bone and cause leukemia. Now, the anxiety from nuclear technology, nuclear radiation, nuclear war really came to a peak in the Cold War. So a lot of the popular culture was reflecting that. Here I show an excerpt from showing how Bruce Banner was turned into the Incredible Hulk when he was exposed to the full force of gamma rays. Of course, in reality, it would have killed him, but that's how things go. All right, so that's a quick tour of the electromagnetic spectrum. We'll now look at some examples of what happens with different colors in light. Look at some of the wonderful things that we can do with that. So let's look at how your eyes respond to light of different color. I'll use another PhET app here. So we will look at different colors of light and how your brain responds to it. Our eyes have 3 different types of color receptors. They'll respond to red, green, and blue light. If I turn on a red light here, then all the photons of red are coming in. My eyes see it, it's red. Okay, that's obvious. If I turn on green, we'll see green. Of course, if I turn on blue, we see blue. Great. What if we get a little bit of both of those? If we turn on red and green, now my eyes are saying, okay, I'm seeing red, I'm seeing green. If I see yellow, well, yellow's in between red and green. It's kind of red, kind of green. That would excite both those receptors. If I'm seeing red and green light together, then okay, maybe that's yellow. If we get all three of them, then I'm seeing the full spectrum of light. That's white light. And we can play around with other combinations. Blue and green together give us something we call cyan or blue-green. Red and blue, your brain says, I don't know what this is. Let's make up something. I'm going to call it magenta. So you can mix light. You can mix the primary colors of light in this way. Now, some of you, I know primary school teachers, you mix paints, you mix with different colors. There you're dealing with something different. Now you're going to be absorbing light and reflecting it back. So yellow paint, your primary color with paint, is reflecting both red and green. If I mix some red in with that yellow, well, then we're going to be reflecting a little bit more red. Here we can see that if I turn down the green, I'll get the equivalent effect. If I turn down just a little bit of that green, now we're reflecting more red. Now we're going to get something. There we go. Yes, now we're getting some orange color from it. On the other hand, if I take my yellow, if I mix some blue in with it, now we're going to start absorbing the red. So if I mix in blue paint, we're not transmitting light, we're going to start absorbing light. If I start absorbing some of that red, most blue is actually a mix of blue and green. So when I mix it, then I start to take that red out. Now we're going to get a lovely green color. And red and blue just does really wonky things. That's how that works. Right, so now we'll take a look at some examples. What happens if we look at colors and then change the color of the light that we shine on it? Here on this whiteboard, you can see all the different colors. I've written the name with the different colors from the markers. And obviously everything looks fine. That's because we're looking at it with white light. White light is nothing but a combination of all the colors of the spectrum. If we make a little tweak now, if I turn off that light and just turn on the red, where'd my red go? We don't see the red anymore because the red is reflecting off the whiteboard. So where we saw red from the red light, it's reflecting that, and the red is also coming off the whiteboard. So the red itself has disappeared. Notice the other colors now. They all look kind of black. We don't really see the other colors. They're absorbing the colors. Green is only reflecting green. It's absorbing the red, and so is blue. So they all look pretty much like black. Let's have a little more fun. Switch over to green. Where'd my green go? Green is gone. Now the red is there, but it looks kind of black. Green has disappeared. Our blue and black are still there. We can bring them all back if we turn on the white. Cool. Okay, so that's a brief tour of the electromagnetic spectrum and all the marvelous properties of light. I love talking about science and education. If you have any questions on any of this, I'd be happy to talk to you more. Carolyn can put you in touch with me. In the meantime, I wish you the best for the coming school year and hope that you can continue to enlighten your students. Thank you very much.